remote sensing. You should know that the human eye, as I mentioned before, is sensitive to wavelengths between 0.4 to 0.7 microns. And not all these wavelengths are equal. We can say that roughly to different wavelengths correspond different colors perceived by the human retina. And we usually summarize that by saying that I will deal with that tomorrow, I think, more precisely. But roughly, we could say that there are three fundamental colors upon which we can build all the others, which are red, green, and blue. And there's a physiological reason why these colors are privileged with respect to the others. And these correspond to three different wavelengths, which we generally identify roughly as 0.45 for blue, 0.55 for green, and 0.65 for red. Okay? Now, let's look at how vegetation behaves. This is the average, let's call it the average curve of vegetation response. It's average because it's not related with any specific type of vegetation. It's how generally, it's about what you generally find with some variations when you look at a vegetation target. And more or less you will find always a shape like this. And it's interesting to see the relationship between the features of the object and the features of the curve. So let's start from this area, which is the visible area. So vegetation behaves like this. You have a minimum here and a minimum here. So reflectivity drops here and there, which means that whatever is not reflected is absorbed. These two dips mean that somehow vegetation sucks energy, sucks radiating power there. This radiating power will not be released back in the atmosphere. So why does this happen? This happens because of chlorophyll synthesis. So there's this substance in vegetation which is called chlorophyll, whose molecule is designed exactly to do that, to absorb the incoming energy, to be transformed in energy usable by the plant. Okay, I think this is quite a common concept that almost everyone knows. Okay, plants work like that. They feed themselves on sun energy, and you can see that on their reflected curve because that missing energy is what has been eaten up by the plant through chlorophyll molecule resonance. Okay, it's fascinating to see. If you look at the chlorophyll molecule, it seems like have been designed to have mass and spring system designed to resonate exactly at that frequency. Anyway, for our practical purposes, what we see is a lack of reflected radiation here and there. Chlorophyll is not as effective around this wavelength, 0.55. Now that's interesting because it means that in the visible range, so what we can perceive with our own eyes, we see reflected radiation which is stronger in the green area. Okay, so most of the radiation in the visible range, which is reflected by the tree canopy, is green or looks green. So we see vegetation green because of chlorophyll. Why? Because of chlorophyll? Because chlorophyll does exactly this job. It kills radiation in the blue and in the red domain and releases green. So when we look at vegetation, we see green. The next interesting part of it, which is not visible to our eyes, but it's very relevant to remote sensing, is that the structure of the leaves is very effective in rejecting near-infrared radiation. Okay, so if you move just one step outside the visible range, you will see a lot of radiation reflected by the vegetative structure. So what is the actual color of vegetation? Vegetation is not green, vegetation is infrared, except we cannot see infrared with our own eyes, so it appears green to us. That's what we can perceive. We don't see this. Insects, for example, typically very good. Insects, animals in general, are typically very good at perceiving this type of radiation because it's survival matter for them. Okay, so I'm telling this because for two reasons. One is even with our own natural remote sensing instrument, we can see some distinctive features of the object that we are looking at. But the other important message is, if you think of remote sensing, when you're searching for vegetation, you shouldn't look for green matter, for green stuff. You should be looking for infrared stuff. Okay, this is so well known that a number of so-called vegetation indexes have been built based on this reflected speed. Then if you broaden your view, you will also realize that, for example, you have two more dips here at 1.5 and 1.9 microns. These are due to resonances in water molecules that are contained in vegetation. So depending on how much water is contained in vegetation, you may have deeper or shallower dips here, but you generally always find them. Okay, so as I said earlier, this is a general shape for general behavior for vegetation reflectivity, but it's indicative, and especially it's very useful to show the concept that if you look at reflectance curve in an optical context, you can learn a lot about the object that you are observing. Okay. So much so that generally, I remember that I told you about pictures and remote sensing data. So remotely sensed data is quite frequently turned into pictures for visual interpretation. So you have the data, which is these piles of numbers, which mean almost nothing to the human sight. So you may find it useful to take this data and turn them into images. We will see later on how it can be done effectively. In these cases, you can leverage the features of remotely sensed data to get a better view of what you're interested in. Like in this case, when you have sparse vegetation, shallow vegetation, not so clearly visible vegetation in a natural, so-called natural color image, where you try to imitate what a human eye would see, you can make it much more visible if you don't represent the greenness of the vegetation, but if you represent the infrared contribution from vegetation. So this is a so-called infrared color image, where you painted red the infrared component rather than the red component. And you see how the same vegetation, which is barely visible in a natural color image, emerges clearly when you leverage the infrared peak. I have another example here, which is typical in the remote sensing community. This is the natural color image of a certain area. It's a university campus with a football field. Everything seems very much vegetated, but if you switch to near infrared, to infrared color representation, you can easily notice that this vegetation was actually fake. Okay, it looked green because it was designed to look green to the human eye, so they made sure there was a peak in the green area, but then what was lacking was the actual infrared response of real vegetation. Okay, this is one more example of, this is a visual example, okay? That's not how you do classification in remote sensing. This is just for educational purposes. How can I distinguish one type of land cover from the other from their different spectral response? Okay. In the optical domain, as you will see, if you reason on microwave domain, then the story is a little bit different. But this is a different story. Okay. False color, right? It was a false color composition. Exactly. Okay. So, one more note which is important to see, already in relation with fusion of data from different wavelengths and what are the features of data from different wavelengths. So we need to reason a little bit about electromagnetic sources. Let me skip some of the physics because we don't have time to look at them, but one very important piece of information here is the so-called Planck law, which may look weird, at least here. You don't need to remember the formula by heart. This is just to say that we have a thing which is called spontaneous emission of radiation. Every body, every physical body at a temperature above 0 Kelvin, so above absolute 0 degrees, so basically including everything, spontaneously emits electromagnetic radiation because of the thermal movement of the thermal motion of its atoms, molecules. Okay, and because of the physics, this takes place with a certain spectral distribution, which follows the so-called Planck law, which depends on lambda and is given for a certain temperature T. So if you change the temperature, the lambda, the distribution of emitted power with lambda changes. Okay. This is the law. This law applies to the so-called black body, which is a theoretical body. You don't find it in the real world, but it's a good basis for discussing real world cases. And I will tell you shortly why this happens. But the basic fact here is that if you raise the temperature, you will raise the amount of radiation which is emitted by the body. Not only that, but you will also change the distribution of distribution of power with them. So it's called spectral distribution of power. And this happens in a manner which we cannot see we don't have time to see the details of this, but we'll go straight to the point. If you think of a body, a black body at a certain temperature, then typically by raising the temperature, you will see the distribution. Distribution always includes a rising section, then a peak, and then a slow decreasing section. Okay, this is how that formula, as it translates into a graph, depends on temperature. So if you change the temperature, you change the curve, but you always have an increasing, a peak, and a decreasing section. Okay, and the peak is higher for higher temperature, and it can grow. So if you increase the temperature, you can start getting a significant emission even in the visible range. So at room temperature, this curve is so low, so displaced to the left, that we don't see any spontaneous emission with our own eyes. Okay, so I just like any one of you, just like all the objects in this room, we are all emitting radiation spontaneously because of thermal agitation. But none of that radiation is visible because the visible component is too low. This curve is somewhere down there. Okay. But if you raise the temperature sufficiently, then you start entering the visible range. And an example is the lamp, which is sending radiation here or showing up in slides. Yeah, that's the result of bringing a small portion of metal to a high temperature. So this is Planck-emitted radiation. Okay. If you walk out and you look up, you will see another big source of spontaneous Planck radiation. It's the sun. Okay, that's where I'm getting to. Now, both the sun and the Earth are good approximations of the Planck of the black body. So the Planck law approximately applies to them. And if you consider, now I switched the graph to the log-log configuration. So you have log wavelength here and log power up there. If you, so this is the shape that the Planck curve, the Planck law takes. If you represent the sun, the temperature of the sun and the temperature of the Earth, you approximately get these two curves. The yellow one and this was supposed to be red. The projector probably is not representing it very accurately. Anyway, this is the sun and this is the Earth. Now, first of all, you may notice that the peak of emission for the sun matches the human eye sensitivity. The human retina developed along the hundreds of thousands of years to be sensitive exactly to the largest amount of radiation available. So basically, the human eye tuned itself to the operation of the sun. That's one fact. But the other important fact is that we do not receive just this radiation, just visible radiation from the sun. The Earth is illuminated by a broad range of wavelengths. Okay? This portion is generally killed by the atmosphere, but this goes through. You remember the optical window, 0.4 roughly to 11, 12, something down there, depending on the area, depending on the atmosphere. Okay. So we should reason on this portion of the spectrum. What happens in that portion of the spectrum? There's an interesting point to see here. And it's the fact that the other player in the field is the Earth itself. Okay? So in this section of the graph, you mostly have a contribution from the sun. The Earth's contribution is negligible, plunges down there and don't notice. But then, if you move to longer wavelengths, then the Earth contribution starts becoming relevant. Okay. This means that when you think of the optical window, you should break it down into two sections. One section, the boundary is more or less, it's conventionally placed at 3 microns, but it's actually blurred. It's very much blurred. One section where you get plenty of radiation from the sun. From the main source of electromagnetic radiation is the sun, and whatever illumination you get, whatever radiation you get from the observed area, it's most likely sun radiation reflected by the object. And the mechanism that you're leveraging is exactly what we saw at the beginning of the lecture. But then there's also another section within the optical window where things work a little bit differently because you have a significant contribution from the Earth itself. This means that when you operate a sensor in this area, you're no longer necessarily looking at reflected radiation. You're likely looking at a significant contribution from the observed object itself. Okay. Now, to cut the story short, when I said when you look at the optical window, you generally see the chemical composition of the object. Now, that's pretty accurate if you think of this section of the optical window. It's no longer accurate if you move beyond 3 microns. And still, staying on the short path, when you look at this section of the electromagnetic spectrum, what you're looking at is the temperature of the object itself. Why? Because, as I said, when the temperature changes, the emission curve changes. In this graph here, I placed a curve related to average temperature of the Earth's surface. But this curve is actually mobile with the temperature, with the actual temperature of the area that you are observing. And since the temperature changes and the emission changes, if you measure the emission, not the reflection, you can relate it to the temperature. This is the so-called thermal remote sensing. If you operate a sensor in this area, it generally means that you are trying to estimate the temperature of the observed object rather than its chemical composition. Okay? So you may remember in COVID times when in every place you had this sort of thermal cameras. Okay? These operate on the basis of this principle. Okay? And this is operationally done also from satellite remote sensing. There are devices which operate in the so-called thermal bands, and these are designed to estimate the temperature of the Earth's surface. But one thing, even at a very shallow level, one thing you should be aware of is that this is a very tricky, slippery type of measurement. In principle, you have a law which connects very tightly the emission and the temperature. So you have the emission, you measure the emission, you have the temperature. But that's not as easy as it seems. There are at least 2 factors to take into account. One is that you still have a contribution from the sun. It's decreased, but it's not over. And the other factor, which is the most difficult obstacle to the correct estimation of the temperature, is the fact that the actual emission depends not only on the temperature, but, look at it, by the reflectivity of the object. So the same temperature translates into very different levels of emission depending on the so-called emissivity, which is the complementary to the reflectivity. So to translate it into easier terms means that when you have 2 bodies at the same temperature, so like a hand and the ring on the hand, which is at the same temperature basically because it's in close contact with the hand, you sense the emitted radiation and you will find very different temperature estimates. But the temperature is the same. Why do you find different estimates? Because the emission that you get from the hand is much stronger than the emission from the ring because they have different emissivities. They have different emissivities because they have different reflectivities. The ring is very shiny, it's very reflective, which drags down its emissivity. So what, getting back to remote sensing, can I measure the so-called surface temperature using satellite remote sensing? The answer is yes, but be very careful. In order to have a reliable estimate, you need to start from very reliable estimation of the reflectivity of the object, which you only have if you know exactly what you're looking at. Does that make sense? So, like for example, Landsat has a so-called thermal band. But the thermal band will provide you an emission value, okay, an emitted power value. But that emitted power value will not relate directly with temperature. You need to add a second component, a second piece of information, which is what am I looking at? Because if I'm looking at, for the same emission, if I'm looking at vegetation, that corresponds to a different temperature than if I'm looking at bare soil. Okay, so that's the main problem with estimating temperature starting from satellite is you need to know what you're looking at. And this is very important to determine. So, thinking back at the scheme I did earlier this morning, we have the optical window and we have the microwave window. Where should I look at for obtaining what pieces of information? And I said optical window, chemical composition. Now I should retouch it to optical window means chemical composition if you look to the left-hand side, but it also may mean temperature if you look to the right-hand side of the optical window. Okay, I think we can skip this. Just one important note here. I mentioned that the atmosphere is important to take into account because if you look at this scheme, you may notice that obviously there are areas where you get completely blank curve. You look at the Earth and it's a black hole. You don't see anything through the atmosphere. But even when you have windows, the opacity of the atmosphere, part of radiation which is absorbed, is not zero, it's greater than zero. So the atmosphere still interferes with the propagation of radiation. Not too much, but still needs to be taken into account. In the microwave domain, it's not a big problem. As you see from the graph, the microwave window is pretty clean, and that the atmosphere won't bother you too much. But if you look at the optical domain, then the atmosphere will bother you, and you have to take that into account in your measurement. So when you work with optical remote sensing, you need to distinguish between the so-called top of atmosphere radiance or sea level radiance, which are respectively the radiance, so the incoming power into the instrument, as measured at the so-called top of the atmosphere, which means I'm measuring whatever powers come from the Earth, and I'm not taking into account that there's an atmosphere there. Top of the atmosphere means that I place myself on top of the atmosphere. So whatever the atmosphere has done to the radiation, it's there. I've done nothing to counteract that effect, okay? As opposed to bottom of atmosphere or sea level radiance, BOA. It's not in the slide, but just make a note of it. Bottom of atmosphere, BOA radiance, means that mathematically, by processing the data, I brought the measurement from the top of the atmosphere to the bottom of the atmosphere. So I tried to make an estimate of what actually happened at the level of the observed object. Okay, this is a very important concept because the difference may be substantial, especially if I have a situation with fog or mist or phenomena like that, where the atmosphere interacts heavily with the reflected radiation. If the atmosphere eats up a part of the radiation, and I do not realize that, I do not correct for that effect, I will be heavily underestimating the reflectance. I will be taking a wrong map, like a worn up key, where a part of the map has been taken away from me. Okay, it doesn't work anymore. So these are important terms to be taken into account when you do practical remote sensing. When you have a remotely sensed data set, you should wonder, okay, what am I talking about? Okay, these are numbers, but maybe other numbers, maybe whatever, but I need to understand what these numbers mean. Have they been corrected or have they not been corrected? Because it makes a lot of difference. Okay, this is something that I get angry at my students about. Are you aware of whether this data is corrected or not? No, sir, I am not. Okay, so go back and get this information, because you have to know what data you're dealing with. Okay, it's not all the same. This difference is something, let me make this one. This difference is something that you may not notice if you're working with pictures. I mean, if you translate the data into an image, you may not be concerned with this difference, because the human visual system is extremely robust. The combination of our eyes and our brain can interpret almost everything. Sometimes it makes big mistakes, but in general, it's very good at understanding what is located, what is there. Okay? But so you don't realize, even if you're working with bad or poor quality data, you may see that it doesn't look very good, but you can still see that, oh, I'm looking at the building, or I'm looking at a water body, and the rest is solid land and things like that. Okay, so great. If you work with pictures and visual interpretation, it doesn't matter. Okay, you can overcome the possible errors in the data thanks to the robustness of your brain, of your interpretation strategy. But be aware of one thing. When you look at pictures, you're throwing away most of the information. Plus, your interpretation capability is limited to a few aspects. Okay, so like you can see you're looking at a building, you can notice you're looking at a water body, but for example, you will never be able to provide a quantitative estimation of how much biomass is contained in that water, or whether the concrete of that building is of a particular type or another, or if it's in good shape or not. Okay, so this is something that you should really keep in your mind. when you talk interpreting pictures and leveraging remotely sensed data are two very different playing fields. They may nurture each other. You may perfect your strategy when you understand what data you're looking at, but one is not a replacement for the other. Okay. Great. Why do we, time is 12, almost 12:45. Okay, so I think, I don't have much time, so let me make an on-the-fly selection for just a couple of things. We have a phenomenon in the atmosphere which is called scattering, and I thought it's interesting. It was interesting to talk about it because it has a direct impact on remotely sensitive data. This is not a distraction of the transiting energy. It's just sending the energy to a different direction, so that the energy that was supposed to reach the instrument is actually thrown somewhere else. It is due to the particles suspended in the atmosphere, and it's particularly interesting to the human beings because this is the phenomenon which gives rise to the blue sky. Okay, so the sky is blue because there's a phenomenon called scattering because of inhomogeneities in the atmosphere. If the atmosphere was not there, the sky would not be blue. If you think of it, there's no reason why we should see blue looking at the sky, because the sky is not blue, it's black, it's pitch black. So it's the atmosphere. And also clouds. Clouds are the result of scattering. And clouds are a blocking factor when you do optical remote sensing. Clouds, given the size of the particles, clouds are very effective at scattering light in the optical domain. So when you operate an optical remote sensing device, if the area that you are observing is cloudy, you don't get any sensible measurement. You do get a measurement, but it's about the energy scattered by the clouds, not by the target that you're interested in. Okay, so you can do the measurement anyway, obviously, but the subject of the measurement is not the intended subject, it's something else. Maybe a subject of investigation in itself, but if you talk about surface, solid earth, sensing, that it's not your goal. So basically what we say is that clouds prevent you from doing remote sensing. It's not 100% accurate, but it's a decent summary of the situation. Now, the same phenomenon doesn't take place when you work with microwaves. So if you switch from the optical domain to the microwave domain, switch to that window, then you don't need to be concerned about clouds because the size of the particle is so small compared to the wavelength, centimeters, to the wavelength in the microwave domain, that this will have no effect on the transiting radiation. A wavelength is a physical length. Okay, and it matters a lot. In the interaction with physical matter, the wavelength doesn't realize the presence of objects that are small compared to itself. So when you work with wavelengths that have the size of centimeters, in the case of microwaves, small droplets which compose the clouds do not have any significant effect on them. Rain may have. If you operate short wavelength microwave remote sensing, like X-band or so, heavy rain may be a problem, maybe, not necessarily. In general, the general rule is if I operate optical sensors, then I have to be concerned with clouds. If I operate microwave instruments, I generally don't. Okay. No. I think we are supposed to stop here at this stage. Just one last note, and then I promise I will let you go. I think this is important operationally. One thing I only briefly mentioned is that we learn, if you use optical remote sensing and we think of right-hand side of the optical window, we get information about the chemical composition of the target because the reflected radiation is basically, it's a flipped copy of the absorbed radiation, and the absorbed radiation is linked to the chemical composition. Okay, great. Why reflected radiation is a flipped copy of the absorbed radiation? Because of the energy balance. Okay, so you have a certain amount of energy power into the reflection phenomenon. Part of the energy is absorbed. Whatever is not absorbed is reflected. So if you have 100 and 30 is absorbed and 70 is reflected back. Fair enough. Okay, and you do that for every wavelength, and you get a flipped photocopy of the absorbance, which you call reflectance, and from reflectance you find the type of object that you're dealing with. But there's an implicit assumption here, which is there's no third way. So the radiation landing on the surface either is absorbed or is reflected. But in some cases, like for example, if you have to do with water, then you do have a third way, which is transmission. Okay, does that make sense? If I look at a reflected radiation on water, I'm not looking at what is not absorbed. I'm looking at what is not absorbed and not transmitted. And transmittance in water is a relevant contribution because water, at least in the optical domain, is transparent, right? So a lot of energy is not absorbed, it sinks into the water body. And so what I measure as a reflection is not directly related with absorption. And this is generally a problem. Okay, so when I do remote sensing on water, I'm not related with absorption, I'm related with something else, which is much more complicated. I have no time to go into the details of it, but just keep in mind that when you work with water, you have a lot of additional problems. One is the fact that you have mirror reflection. So you get either no reflection or too much reflection, independently of the particular body, plus radiation that sinks into the water body then may come up again reflected by, for example, suspended matter or things like that, which is at the same time an opportunity because you can measure the contribution from suspended matter and estimate how much, for example, algae bloom may be there. But at the same time, it's a heavy disturbance for your measurement. So water is a very specific case, and it should be treated differently with respect to other types of land cover surfaces, which in fact has a branch of remote sensing of insulin. Okay, so I think we should stop here for this morning. Thank you again for bearing with me in these first 2 hours. I hope you didn't get too much bored. I appreciated the questions that you have asked. Please keep asking questions, because this gives me the opportunity to go a little bit deeper into some topics. We don't have much time, so we don't see everything. I'm really skimming very, very quickly, and I would leave to the questions and to the offline discussion after the lectures the possible other needs of deepening that you may have. Okay, so again, thank you, and we reconvene here at 2:15 p.m. Okay? Have a nice lunch.